these mathematical models. Okay, error analysis is a different set of slides. It's a different set of slides. Okay, so that one is also posted on e-learning. Again, because we have problem with e-learning, I think early in the semester, a lot of problems with e-learning. Not stable langsung, it's not stable. Okay, so we are going to talk about physical laws and conservation laws and engineering. So remember that I told you last time in our first class about cognitive level 1, level 2, and level 3. We were talking about what is Newton's third law, right? What is Newton's third law? And I gave you an example where we use Newton's third law in our statics, right? In our statics. So this is part of the mathematical modeling in engineering. So we need to understand what is the physical law, which is that is applicable to our problem, and then how do we use the physical law, okay, in engineering. So this is what we are going to talk about. Okay, can you hold on for a second? Let me do something else here. I need to open up a piece of paper so I can write. Okay, let me share you my piece of paper. Share. Okay, so this is one. Okay, so this is the other one. So all right, so let's look at the physical law. Let's look at this one here. Okay, so let's go to the next slide. Is it went the other way around. Okay, all right. So what we have here is a mathematical model. It can be represented in form of dependent variable is a function of something. For example, let me show you. Okay, let me show you using my piece of paper here. For example, you normally see that y is equal fx, right? This is what you normally see, right? I think this is a lot in you see in math, you see in engineering, and so on. So this is just a mathematical expression that says that y is a function which depends on x, right? So for one, is this. So this is our x, and this is our y, and this is the function. So the value of y will depend on this line where, and the value of y will depend on this line and where x is located. When x is, let's say, x1, the value of y is this, right? When using this function, where y value will change when x is at a different x. For example, this is y2, so this is y1. So this is what it says. This is what it meant when it says dependent variable. So in this case, which one is the dependent variable? Anyone? Anyone? No one?
Why?
Please say, because my screen is full. I cannot see your chat box. Please turn on your mic and speak.
Why?
Y depends on x. How does it depend on x? According to a certain function, right? A certain function. So in this case, you can see that the dependent variable is x. Okay, dependent variable is y, and the independent variable is x. Does x depends on any value? X is x. It is independent, right? It is independent. Okay, there are other things here. it can say what is independent variables, what is parameter, what is forcing function. For now, I just showed you one example, which is an independent variable. So in our case, y is our dependent variable because it depends on x, and x is what we call it independent. It does not depend on anyone, on anything. And the relation between y and x is related through a function. Okay, so this is what it meant. Okay, this is what it meant. So this is just like learning refresher course on your mathematics. So this is some of the definitions. Definition of what is a dependent variable, characteristic that usually reflects on the state of the system. Okay, this is from your textbook. If you read a textbook, this is chapter 1, I think 1.1, if I'm not mistaken. Okay, 1.1, if I'm not mistaken. An independent variable dimensions such as time, space, along which the system behavior is being determined. For example, I want to determine what is the y1 value. Okay, y1 value determines, it depends on x1 according to this function here. According to this function. Okay, so the independent variable is this, and the parameter reflect the system properties or composition. I think I'll show you both of these things, both parameters and forcing function. I will show you using an example later. I think in this slide I have some examples. Okay, so this is the easiest one. Basically, y is a function of fx. So y equal to fx. Right, so let's go next to next slide. Just this one. So conservation law. Conservation means it conserves, right? So conservation law are the most important and fundamental laws that are used in engineering. For example, we know that change is increase minus decrease. That's a change, delta. Basically, this is a delta. So bila ada change mean normally there's a delta. Change in time, basically, for example, change in time is T2, T1 minus T0. This is initial time. This is the current time, for example. So this is the change. Okay, but remember that change implies changes with time, transient. If change is not existent, this is what we call non-existent mean steady state. For example, if we fall from an aeroplane, initially our velocity with respect to time, okay, initially it will increase and it will hit what we call a transient value. So transient mean in this case, this is what we call the transient value. Why? Because in this case the velocity keep changing with time. Okay, but at this one, the velocity, basically, let's say this is V4, maybe Vn, this is Vn minus 1. Okay, so Vn minus 1 equal to 0. So basically, this is a steady state. There's no change in velocity. But in this case, for example, we have Vb, and this is Va, and the change of velocity is just Vb minus Va, and this is not equal to 0. This is what we call a transient state. Transient. Okay. Okay, so I had received a lot of Telegram messages. All right, so this is just the conservation law. So conservation means, in this case, there's no, we conserve mean this is the case. There's no change. Okay, there's no change in the value. I mean, there's no increment or there's no decrement. So this is what we call steady state or conservation, conserve. Okay, for example, energy conservation. I remember when I was doing my PhD, my professor told me there are 3 things that you must know in, in engineering: conservation of mass, conservation of energy, and conservation of momentum. 3 things. Right, so this is one example. This is one example. So in this case, we see that our steady state, it says a steady state, which means steady state means there's no change, right? Steady state, that means there's no change in the fluid flow. For steady state, incompressible fluid flow in pipes. So flow in must equal to flow out. So this is the flow in, 80 and 100. So whatever comes in this case 180, must equal whatever is coming out. Okay, whatever is coming out. So based on this, we know whatever coming is 100 plus 80, which is 180. And of course, we know one of these is 120. So what is the pipe flow? What is the flow for pipe number 4? So basically, the flow in must equal to flow out. And when you do the conservation of, in this case, fluid flow, then you get 60, because this is 100 plus 80 must equal 120 plus 60, and both sides are 180. Right, so this is one simple application of conservation. In this case, conservation of flow. All right, so this is Newton's second law. This is Newton's second law. States that this is definition. I think in my lecture last time I was talking about Newton's third law, right? In this case, we are talking about Newton's second law. So where is Newton's second law used in your study? Can you tell me? Anyone, please?
Dynamics.
Yes?
Dynamic.
Dynamics, right? So now you know 2 things. Now you know 2 things. So summation of forces equal to 0, right? This is for what law?
Static.
Static. No. I'm talking to you. The law. What law? I'm asking you about the law, not the subject. What law is this? Summation of force equal to 0.
Newton first law.
Newton? First law?
First law. Is it first law?
I'm asking you and you asking me back. Don't ask me that, please. I'm asking you. Huh? Nurin?
Newton law.
Newton?
First law.
First law. Tadi Ifat pun kata Newton first law. No. This is wrong. This is summation of force equal to 0 is for class static, which is the third law. Third law. Third law. Newton's third law. So this is for your statics class lah. Okay, if you attend my lecture last time, last lecture, you know why summation of force is equal to 0 is Newton's third law. Why? Because Newton's third law says that for any action, so let's say this is our simply supported beam. Okay, let's say the action is here, F, and the distance is L over 2. The other side is also L over 2. So total distance, total length of the beam is L. So this is F. So the question is, what is R1 and what is 2? Can you see this is a static problem? Right, this is a static problem, right? No movement at all. So Newton's second law says that for any action, the mass E equal and opposite reactions. Okay, so the first requirement, it must be equal. The second requirement, it must be in the opposite direction. Okay, so in this case, look, we know we have an action going downward, right? And because of the force that is going downward, so we have reaction going upward. Okay, so this is R1 and this is R2, right? So we satisfy or we fulfill the first requirement, which is, or the second requirement in this case, opposite. So this, the reaction is in the opposite direction of the action here. Okay, so that's one thing. The other thing is that it says that the reaction must be equal to the, in magnitude, to the action. So in this case, we know that R1 plus R2 equal to F, right? So how do we write this in terms of mathematical formulation? So what I'll do here is summation of forces upward as positive. Okay, and what is the forces here? The forces here is R1, which is upward as positive, plus R2, again upward is positive, minus F, because F is going downward, right? And it must equal to 0. Why? Because according to Newton's third law, that the total reaction must equal the action. The total reaction must equal the action. So in this case, if this and this are equal, then this minus this must equal to 0. So in static, basically summation of forces must equal to 0, which complies to what we call Newton's third law. Okay, Newton's third law. Okay, now what about Newton's second law? So I hope this is clear. This is another law that we use in our engineering analysis. Okay, so in this case, this is our Newton's third law, right? Newton's third law. Right, any question about Newton's third law and its application in statics? I hope this is very clear to you, yeah? Okay, no problem. Boleh ya?
Clear, Doctor.
All right, thank you very much. All right, so the next one is Newton's second law. So Newton's second law is basically saying that summation of forces must equal to ma. But what is the acceleration value here? What is a here? What is a?
Difference change in velocity.
Change in velocity, right? So over time, change in velocity over time, yeah? Because acceleration is defined as change in velocity, yeah? With respect to time. Then what you get is velocity, so the meter per second, right? And time is also in second, then meter per second square. Just like your G, which is 9.81 meter per second square. So G is also your acceleration. Okay, this is what we call acceleration due to gravity, right? To gravity. So now the next one is note for static problem, what is the velocity? Any velocity?
0.
Oh,
0. So when velocity is 0, what is the acceleration?
0.
0. So this becomes 0 for static problem. So, right, because A is 0, right? In static problem, A is equal to 0 because there's no change of velocity over time, right? So Newton's third law can be reduced to Newton's second law when there's no change in velocity with respect to time. So if you look at this, it says that states that the time rate of change of momentum, mv is the momentum, right? So d dt is the change with respect to time. So if m is constant, if the mass is constant, then the only thing that change with respect to time is v. So it becomes ma, right? So this is the Newton's second law. So I think somebody mentioned that we use this a lot in your dynamics class, right? in your dynamics class. Right, so this is Newton's second law of motion. So let's go to the next one. Yeah? So formulation of Newton's second law has several characteristics that are typical of mathematical models of the physical world. Remember, note that this physical law describes physical problem in terms of mathematics, right? For example, our physical problem, let's say this is the one. This is one of our physical problem, right? So using the law, in this case, using Newton's third law, okay, in our static problem, what we can relate is we can convert that physical problem into mathematical problem, right? So in this case, remember that for this problem here, we have two unknowns, right? We have R1 and R2. Right, so this is just another mathematical problem. So can we solve for R1 and R2? If we know what is F and we know what is L?
Yes.
Yes. So how do we solve this? How do we solve this? Dah lupa dah. Oh, doktor, saya ambil statistik 3 tahun lepas. Dah tak ingat dah. This is always the excuse. The excuse.
The force times the length over 2.
Okay, so before you start doing all that, think. Okay, how many unknowns do we have here?
2.
2 unknowns. Which are?
R1 and R2.
R1 and R2.
Okay, R1 and R2, right? So no question. So we know that there are 2 unknowns, which requires how many equations?
2 equation.
How many?
2 equation.
2 equations, right? So when you have 2 unknowns, you need 2 equations. Right? So what is the first equation then?
Total force equal to 0.
Okay, so this is one of them, right? This is one of them. Right? Because this comes from this requirement, right? Am I correct? So
Yes.
we have one equation. So what's the other one? What's the other one?
Moment.
Total moment equal to 0.
Is moment a force?
Rotational.
Remember, it says that for any action, there must be opposite and equal reaction. For example, in this case, we already have one equation, which is R1 plus R2 equal to F. The next one is we need to find another equation because we are not able to solve 2 equations with only one unknown. 2 unknowns with only one equation, right? So we need another one. So in this case, we know that the summation of forces is this, right? This is one equation. And the second equation is summation of moment at, let's say, point 1. Let's say this is my point 1 and this is my point 2. Point 1 equal to 0. Note that if you look at this problem, maybe I draw this here. So this is my point 1. So we have R1 here, and we have R2 here, and we have the force here. Okay, so we say that summation of moment at point 1 equal to 0. And I assign that for a clockwise rotation as a positive moment. Right? So in this case, F1 times L over 2, sorry, not F1, F times L over 2 will cause a clockwise moment, which is a positive, right? But R2 will produce a moment this way, right? Minus R2 times, what's the length here? L2 plus L2, right? Which is L, and this should be equal to 0. Note, in the second equation, how many unknowns do we have? This is the second equation. The first equation, we have R1 and R2 as our unknown, right? So we cannot solve it. So we need another equation. So in this case, how many unknowns do we have? In
1.
the second equation.
R2.
Only one, right? Only one. Can we solve for R2? Can we solve for R2 here?
Yes.
Yes.
Yes. So in this case, R2 is equal to F over 2. Now, since we already know what is R2, this is already known, what we are left only with one unknown in the first equation. Can we solve for R1?
Yes.
Yes. So R1 is, of course, F over 2. Okay. So this is how you use math and physical law solving engineering problems. Okay. So this is the idea. Okay? This is the idea. So my son, anak saya, Form 4, was asking me about what does engineer do. Jadi kan engineer kan? Jadi buat apa ya? It's really hard to answer the question. So I tell him lah, I do this, I do that. I think one of my biggest achievement is writing a standard for Petronas. Design for offshore structures kan. So, oh, dia dibuat tu. Yes. I'm not building it lah, but I set the standard, all the calculations. So that was one of the, I think the highest achievement lah saya pernah buat. Right, so now we know that we can use physical law because we use physical law to model a physical problem. Okay, and then from the physical law, we can solve using mathematics. So this is one example that how we have a physical problem using a physical law and mathematics to solve for what we need. In our case, in this case, we have R1 and R2 as our unknowns, right? And we are able to solve this. Right, so this is the basic idea of using physical law and math to solve engineering problem. So remember, to me as an engineer, okay, you are the user of physics and mathematics, or in general, sciences and mathematics. Of course, when you go to fluid mechanics, you have another law, another set of laws. Okay, if you go to thermodynamics, you have another law. First law of thermodynamics, second law of thermodynamics, and so on, right? So the same thing here. So I'm a solid mechanics person. So this is I can talk about this because this is my area. All right, so it describes the natural process or system in mathematical terms. So we described that. For example, just now, our beam problem. It represents an idealization and simplification of reality. Okay, this is tricky. Is our calculation exactly the same as what is expected in the real world? What are the assumptions in doing beam analysis? What are the assumptions? If you do remember sigma equal MC over I, this is from your solid one. This is from your solid mechanics one. Okay, so what are the assumptions for this bending moment? Sorry, bending stress. Okay, so if you look at the laws, for example, what we use now is what we call Euler beam. Euler's beam formulation. And of course, there are other beam formulation. For example, Timoshenko. Timoshenko beam formulation. So which one is more accurate? Is it Euler's or is it Timoshenko's? Okay, for your information, Timoshenko's beam calculation formulation is much accurate. It's more accurate than Euler's, but Euler's is easier to calculate. But Timoshenko is not only hard to calculate, but I think the accuracy is only improved by a certain percentage, by a small percentage. So a lot of work, but small gain. So people say, okay, why not just use Euler's formulation? It's easier, even though it has some errors because of the idealization. Because when we idealize, we say assume that beam is prismatic, assume that beam is homogeneous. But in real world, is your beam totally, purely homogeneous? No, right? So
No.
these are some of idealization and simplification. But how do we avoid this kind of errors, these calculation errors? How do we avoid this? How do we basically not avoid, but overcome this kind of errors in calculation? So when you design something, you put what you call safety factor, right? Remember safety factor? Again, in your design class, component design class. N equal to 2, N equal to 1.5, and so on. So this is how we cover up all the simple idealization and simplification in our errors due to all these two things, these two problems, idealization and simplification. Finally, it uses reproducible result. Consequently, it can be used to for predictive purposes. For example, in our beam problem just now, we can always use at least these two: summation of forces equal to 0 and summation of moment equal to 0. So we use it multiple times because it can give us reproducible results. Basically, our Newton's third law just now. Okay, so because of that, we use it for other problems. All right, so now the next one is, the next one is this one. Okay, complex model require advanced mathematics. Some mathematical models of physical phenomena may be much more complex. Okay, so remember the type of mathematics you have learned so far. Kita ada algebra, right? Basically, our problem just now involve algebra, right? Of course, we have calculus, right? Calculus, which is what? Which is basically our dy dx, kan? Dy dx integration and so on. And in calculus, we have another field, which is what we call the ODE and PDE. What is ODE? Can anybody tell me what is ODE? Ordinary differential equations. What is ordinary differential equation? I think you have taken this. I think SCE 1793, if I'm not mistaken. What's this? What's the term in Malay that you, I think you took the class already. This is what we call the persamaan.
Terbitan?
Yes, persamaan terbitan. Okay, you've taken this. And it's not easy to solve that kind of mathematics, right? Of course, we have another, we have statistics, probability and statistics. Okay, a lot of other things lah. Okay, so this is simple, this is not as simple, right? Okay, so I remember my professor told me when you are doing problems, real world problem, normally every basically he told us in class that if you can model normally natural problem, real world natural problem can be described by PDE, partial differential equation of the second order. So when I did my master's and PhD, we do a lot of this kind of math, PDE second order, because we want to model it. Actually, it can go higher than that, but again, we say we simplify a lot. We simplify a lot. Okay, we simplify a lot. So some mathematical models of physical phenomena may be much more complex. So this is one of the examples. Yeah, I told you just now that we may need to use PDE of the second order, and it's not easy to solve that kind of problem. Complex model may not be solved exactly or require some sophisticated mathematical techniques than simple algebra for their solution. So this is where we use numerical methods because it's not easy to solve it analytically. Yeah? It's not easy. It's not easy. So we use numerical method as an alternative. Again, if you remember my first lecture, I told you when we use numerical method, we are introducing errors to the calculation. Eh? The problem here is how much error can we tolerate? Can we tolerate? Is it 10%? Is it 5%? Is it 20%? Or is it 1%? So this is the decision that you have to make. Eh? So the next slide is this one here. So how do we solve this? Eh? Anybody? Anybody? Can you solve this? What law are we going to use here? Any idea? Any idea? Huh? Tak dengar, sorry.
Conservation of momentum.
Newton law, which law?
Second.
Conservation of momentum. Newton? Second law.
Yes.
Okay, so again, back to our engineering analysis. So back to our engineering analysis, this is a physical problem. So basically you have a parachutist, terjun daripada kapal terbang, jumps out and a helicopter, ke plane, ke whatever. And when he jumps, what happens is that it has a velocity. It has a velocity. So what is the velocity of that parachutist? So what we need to do is, again, we need to draw the free body diagram, apply the correct physical law, okay, and then when we have the equation, when we use the physical law, we will have an equation, a mathematical equation, and then solve the equation, right? Solve the equation. So in this case, let's say we have this parachutist. Okay, saya tak pernah lukis orang lah, boleh lah macam ni. So dia terjun. Of course, there's a force pulling him down. Okay, so FD, F downward. And of course, because of the drag, okay, of the wind drag, there is a force that will push him upward. So one is pull, one is push. Sorry, one is pull, one is pull, one is push. Okay, so this one is pushing, is basically pulling him downward because of the gravity, right? And this one is pulling upward. Okay, so we know summation of forces, summation of forces. So we have summation of forces in this case is summation of force going upward. So again, in this case, I'm using upward as a positive value, minus FD. And okay, F upward is CV. This is what we call the drag, drag force. And this is our FD is just our mg. This is what is this mg? What is mg?
Gravitational force.
Nurin tak dengar. Kuat sikit Nurin.
Mass times gravitational force.
So what do you call that force?
Weight.
9.81.
Weight, okay.
Weight.
Right, so all right, so in this case, what is the value here? What is the value? Is it 0? Is it something?
9.81.
No. I mean this equation. What should it equal to? The summation of forces. 0.
Yes.
Okay, so Nurin said 0. So what about the other? Anyone?
MA.
MA. Why MA?
Because moving motion is not on statistic motion.
Statistik tu lain. Statik lah, bukan statistik. Statistik tu yang...
Sorry. Equal to 0.
Equal to 0. Okay. Alright, so now, is it equal to 0 or is it equal to something else? So what's the difference between summation of forces equal to 0 and summation of forces equal to MA in this case? I know the first thing is that we are using the different Newton's law, right? So summation of forces equal to 0 is basically Newton's third law, right? And summation of forces equal to MA is Newton's second law. So which law are we using here? Which law describes this physical problem?
Oh,
Second law.
Second law.
Second law, right? So what is second law? Second law says that, okay, just in case you have forgotten, let's go back here. Yeah, this one. Change of momentum, right? Change of momentum. That's the time rate change of momentum of a body is equal to the resulting force acting on it. So basically, this case, because the parachutist is still moving from when he jumps from the plane, is still moving sampai dia hit the ground. Kalau dia tak buka parachute, dia akan hit the ground dan apa jadi? Matilah. Most probably matilah. Right? Okay, so if you say that the summation of this force equal to 0 means apa yang berlaku tu? That guy will be, it's not going up, it's not going down. So what happened? It's floating. It's floating. Betul? Is that true?
Yes.
When you jump out of an aeroplane, will you float?
No.
No, you keep falling down, kan? So in this case, the correct or the applicable physical law for this problem is Newton's second law, right? It's Newton's second law. So let's write this. Okay, so this is the equation, and we know that in this case the summation of forces must equal to MA. So basically what we can get is KCD minus MG. Oh, sorry. Let me rewrite this. Let me rewrite this. This is tricky. This is tricky. So before that, we need to know what is G. G is going downward, right? G is going downward, right? Betul tak? Am I correct? G is going downward. G is not going upward, right?
Yes.
So what I'll do is I'm going to change the equation. I'm going to change the equation. So in such a way that I'm going to use my formulation here, my direction here. Positive is downward. So positive is downward because MA is going downward. Let me double check. I don't want to confuse you, but okay, so why don't we stop here? Okay, anyway, time is up. Do you have any other classes after this?
Yes.
Okay, so since we have class, so I think I need to stop here. Okay, maybe you can continue later, or I'll announce to you, because I think I have a video on this. I have a video already on this, the link to my YouTube video on how I solve this problem. Okay, so now let's stop here, and there should be a homework that I assigned to you on e-learning. When e-learning is back up and stable, I'll let you know, okay? All right, so thank you very much, everyone. So we see you again on Sunday. We see each other again on Sunday. So that's it. So have a nice weekend, everyone.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Doctor.
Thank you, Doctor.